Now that we learned about basics of transport layer and basics of reliable transport, it is time for us to start exploring the Internet's transport layer protocol that provides reliable data transmission, TCP. TCP is point-to-point. It has one sender and one receiver within a single connection. It is connection-oriented, and once the connection is in place, it delivers in-order byte stream within the connection. It offers reliable in-order byte stream. Means we measure the bytes in the fly, not the number of segments. It is a pipelined reliable protocol with congestion and flow control affecting the window size. And it supports full duplex data delivery with maximum segment size, or MSS, determined by the link layer maximum transmission unit, or MTU, which is 1,500 bytes normally, with exception of jumbo frames. It is flow controlled, meaning that the sender will not overwhelm the receiver. That is TCP in fast bullets. It also offers some more, but let's dig in and see what each of these items mean in detail. Let's start with taking a look at the TCP segment structure. TCP header, like UDP header, has a source port number, destination port number, and the checksum fields. These are used for multiplexing and demultiplexing and error detections, as we discussed. It also has sequence number and acknowledgement number fields, as well as a control bit A showing if the current segment's acknowledgement number value is valid. Additional TCP options that could be of variable length are at the end of the header and right before the data payload. Therefore, the header length is variable and there is a need for a field to determine it. Connection management of TCP that we will see later is done using RST, SYN, and FIN bits. Receiver window field is used for flow control. CNE bits used for congestion notification also will be discussed later. There is a number of additional control bits that we will not discuss here, but you can find further details by reading RFC 793. Remember the window discussions we had in RDT pipelining. TCP is a pipelined reliable transport protocol, and it uses sequence numbers and windows to have control over the segments on the fly. Sequence number in the TCP segment is used for this purpose. It shows the byte stream number of the first byte in segment's data. Acknowledgements coming from the receiver include the sequence number of the next byte expected from receiver side and contain cumulative ACK for received segments. TCP RFCs do not specify handling of out-of-order segments, and it is up to the implementer to decide what to do. Let's take a quick look at the sequence numbers in a very simple TCP connection scenario. Imagine we have two hosts A and B within a TCP connection. User at host A types C. That is the very first data we want to send to host B in this connection. The initial sequence number in TCP communication is picked in random. Assume in this scenario, this sequence number for communication of A to B is 42, and for the communication from B to A is 79. Remember that this sequence number is byte sequence number in TCP, meaning that now host A is starting the communication with byte 42 and acknowledging that it will be expecting byte with sequence number 79 from B. When C is sent from A to B with these sequence numbers, letter C is 1 byte. Therefore, the sequence number will increase by 1 in the next communication. Assume that B will echo a C as well. The communication from B to A will include sequence number 79 as of previous announcement from host A. It will also include ACK equals 43 because it has received byte 42 with C, letter C, from A, and now will be waiting for byte 43. If A receives letter C and echoes another letter C, the communication will continue with sequence number 43 and ACK 80. Note that the acknowledgements are not separate segments and are included in data segments here. This is called piggybacked ACKs.